Hello and welcome to all students in this my YouTube channel. Now students, we are in the topic of transition and inner transition elements. Now students, in this topic, in our today's lecture, we are going to learn the comparison with S block elements. In our previous lecture, we have seen some introduction about the transition elements and their different physical and chemical properties also. With the help of graph, also we have studied some ionic radii and atomic radii also. Now students, this is the important point, that is comparison with S block elements. In this our slide we are going to look at the property which is we have placed in one column and with transition elements and one of the elements of S block element, that is calcium. Now if you look at the melting point of transition elements, it will be very high, that is over 1000 degrees Celsius. But if we consider for S block element, that is calcium, it is lower than the transition element, that is 850 degrees Celsius for calcium. Now the density, if you look at it, it will be very high for transition elements, but it will be very less, that is low for calcium. Atomic radius, which is smaller than that of the calcium, but if you look at for S block element, that is calcium, it will be larger than that of the transition elements. Ionic radius, if we now going to talk on this point, it will be smaller than the calcium for in the transition elements, but here larger than the transition elements. Again, if we are going to focus on the first ionization energy, it will be larger than that of the calcium, and for calcium small, that is S block elements, smaller than that of the transition elements. Now one of the important point, that is electrical conductivity, it will be a good but poorer than that of the calcium. If you are going to talk about the transition elements, now for S block elements, that is calcium, it will be a very good, better than that of the most transition elements. Now students, variable oxidation states for transition elements. Now we are going to learn. Transition elements have variable oxidation states in their compounds. For example, if you look at for iron, it will show Fe2 plus and Fe3 plus, that is their corresponding compounds also. The variable oxidation state is due to the small energy difference between 4s and 3d subshell. Now that small energy difference will form the different compounds. Now Fe has oxidation states like this, ranging from +1 to +5, sometimes +6 to. Now out of all these oxidation states, only +2 and +3 are common, that is most Fe ions will show this stable +2 or +3 oxidation state. Compare the ionization energies of Fe and Mg. If you look at here, element, that is Mg and Fe, we have considered here. The first ionization energies are now we are going to learn here. For Mg it will be 736 and for Fe it will be 762. And if we lose the second electron, we require this much amount of energy, and for third electron we require 7740, this much amount of ionization energy, and like that of fourth one. So if you are going to compare for Mg and Fe, for Fe the ionization energies, means the electron which is now going to, means the energy required to lose the electron from its outermost shell required, it will be less for Fe than that of the magnesium. Now when the compounds are formed, energy is needed to remove the electrons from the atoms. The energy of this ionization is supplied by energy given out when the new bonds are formed. So this is very important point. According to the variable oxidation states, means the energy for this ionization is supplied by the energy given out when the new bonds are formed. Let us see for Mg. Mg2 plus ions are easily formed when Mg forms compounds. For example, when Mg2 plus ions and O2 minus ions form electrovalent bonds, energy liberated is enough to supply the ionization energy to form Mg2 plus. But the energy liberated is not high enough, that is 7740 kilojoule, to remove the third electron from the inner shell. Hence Mg can only form Mg2 plus ions. For Fe, that is iron, if you look at here, Fe2 plus ions are easily formed when Fe forms compound, but there is no big increase in the third ionization energy, that is from 3d subshell, due to small energy difference between 4s and 3d orbitals. Now energy released in the formation of Fe3 plus, that is compounds which are formed by when Fe has plus the oxidation state, the compound must be enough to remove the third electron from the Fe3 plus ions. Now the same applies to the loss of more electrons to form higher oxidation state compounds of the iron, though it is rare in the case of iron. Now students, if we come to the next point, that is oxidation states in compounds ranging from scandium to zinc, that is variable oxidation states. Increase in maximum oxidation state, decrease in the maximum oxidation state, that is oxidation number. If we consider the circled oxidation states, these are the elements which shows their common oxidation states, and if we consider here, the lowest oxidation state is shown by some elements, that is +1, and the most common elements among all these is nothing but the +2 +3, means the maximum number of elements which shows the +2 and +3 as a common oxidation states. And among these, some questions may be asked in your theory as well as CET, as well as some competitive examinations, will be like this: which is the element which shows the maximum oxidation state in the 3D block element, or the first row of inner transition elements, which is nothing but the manganese and has the maximum oxidation state, that is +7. Variable oxidation states arise from the similar energies required for the removal of 4s and 3d electrons, means similar energies which are required for the removal of 4s and 3d electrons. The maximum oxidation state of an element corresponds to the maximum number of electrons available for bonding. For example, maximum oxidation state for chromium is 3d5, all 3d5 and 4s1 electrons used in the bonding, that is chromium has 6 electrons available for bonding. All have the M2 plus ions, that is except the scandium, that is M2 plus, that is common oxidation state. Stability of the +2 oxidation state increase across the row marked increase in third ionization enthalpy. Now the maximum state increases from scandium to manganese and decrease from manganese to zinc. This is due to the decrease in number of single electrons in the 3D subshell, and the 4s electrons, that is maximum of 4s electrons has the completely filled orbital. From Mn to Zn, that is manganese to zinc, some electrons in the 3D subshell are paired, or we can also say unreactive and not used in bonding. Now students, these are the different atoms which shows the different variable oxidation states. Now the use of transition element ions in redox reactions. Some examples we have mentioned here. Commonly forms the compound with oxidation state +2 +3. Solutions of Fe2 plus are readily oxidized to Fe3 plus by many oxidizing agents such as K2Cr2O7. For example, redox reactions we have shown here, and the EMF which is needed for this conversion will be shown here also. Solution of Fe3 plus readily reduced by many reducing agents including Ki. These are the some common examples. So this is all about in our today's lecture. In our next lecture we are going to learn the formation of complexes. Thank you very much.